In this video, we will cover Chapter 8, Section 2, Testing a Claim about a Proportion. So this section describes a complete procedure for testing a claim made about a population proportion P. We illustrate hypothesis testing with a p-value method, the critical value method, and the use of confidence intervals. The methods of this section can be used with claims about population proportions, probabilities, or the decimal equivalences of percentages. There are different methods for testing a claim. Part 1 of this section is based on the use of a normal approximation to a binomial distribution, and this method serves well as an introduction to the basic concepts, but it is not a method used by professional statisticians. Part 2 discusses other methods that might require the use of technology. So we are testing a claim about a population proportion. The objective here is to conduct a formal hypothesis test of a claim. Some notation, you should already know these. N is the sample size or number of trials of your sample. P is the population proportion, and it's also the value used in the statement of the null hypothesis. P hat is the sample proportion, which is X over N. Q is going to be 1 minus P, and also just note that X is going to be equal to N times your sample proportion, where X is going to be the number of successes within your sample. So the requirements. In order for this to work, you have to have the sample observations must be simple and random, and the conditions for a binomial distribution are satisfied. Remember, binomials there are a fixed number of trials. The trials are independent, meaning if you say yes, that will have no bearing on if I'm a yes. Each trial has two categories. It is either a success or a failure. Can't be somewhere else, somewhere in the middle. There can't be a third option. It's either yes, no. It's Boolean. And the probability of success remains the same in all trials. The third condition is that N times P must be greater than or equal to 5, and N times Q must be greater than or equal to 5, so that the binomial distribution of sample proportions can be approximated using the normal distributions as described in Chapter 6, Section 6. Testing a claim. The test statistic for testing a claim about a proportion is given by this formula. This formula was first introduced in the previous section 8.1, and it is saying that the z-value, which is the corresponding score given the sample proportion values, and it is equal to p hat minus p divided by the square root of p times q over n. P-values are automatically provided by technology. If it is not available, then you can use Table A2 and refer to Figure A3 on page 364. And then for critical values, you can use a standard normal distribution from Table A2. Remember, there are two ways that we are going to be solving these. When testing claims about proportions, the confidence interval is not equivalent to the p-value and critical value methods, so the confidence interval method could result in a different conclusion. Whereas the p-value method and the critical value method, they're going to give you the same value. So it is recommended you use the p-value method or the critical value method for testing the claim about proportion. But we'll show you all three methods anyway. So example, we are making a claim. Same one as the previous example. Most consumers are uncomfortable with drone deliveries. Now we will do this problem in its entirety. 1,009 consumers were asked if they are comfortable with having drones deliver their purchases, and 54% responded no. Use these results to test the claim that most consumers are uncomfortable with drone deliveries. We interpret most to mean more than half or greater than 0.5. So do more than half the entire population have an issue with drone deliveries. First, we have to do a requirement check. The 1,009 people, okay, they're randomly selected. So that's good. 2, there is a fixed number of independent trials. Your neighbor saying they're okay with it should have no bearing on you if you're okay with it. And then 3, n times p and n times q are both greater than or equal to 5. So we have enough successes and failures in order for us to be able to use this distribution. So the 3 requirements are satisfied. Boom, we're good. Okay, now we are going to do the p-value method. We'll use technology for this part. So here's how you will do this using your TI calculator. You're going to press stat. You're going to hit the right arrow to go over to tests, and then go down to where it says 5, or you can hit 5, or you can go down to where the 5 is highlighted, where it says 1 prob z test, and then hit enter. And then you're going to enter your value. P naught is going to be your null hypothesis claim. X is going to be 545, which is the number of successes from the sample. Your sample size, n, is 1009. And your probability, you're looking for when it's greater than the p-value, since H1 is stating that the population proportion is going to be greater than 0.5. Press enter on the word calculate, and then you should get this value over here. I encourage you to just do this now to make sure that you know how to use your calculator correctly. You can also do this by hand using the table. So figure 8.1 on page 360 lists the steps used for the p-value method. So using the steps from that figure, we can test the claim as follows. Step 1 is saying the original claim is that most consumers are uncomfortable with drone deliveries. So that would be in symbolic form, p is greater than 0.5. The opposite of that claim would be p is less than 0.5. Or sorry, p is less than or equal to 0.5. Next, we can create our 2 hypotheses. The null hypothesis always has the equal sign, so we'll say the null hypothesis is p is equal to 0.5, and the alternative hypothesis is going to be p is greater than 0.5, our original claim. So for the significance level, we'll select 0.05. Usually your problem will tell you what to use. If not, you can do 0.05, but I'll make sure that you know what you have to do. Step 5, and again, these are the same steps that we introduced in the previous section. Step 5, because we are testing a claim about population proportion, the sample statistic p hat is relevant to this test. The sampling distribution p hat can be approximated by a normal distribution. So we will use the formula for a z statistic, and then we find that it is going to be equal to 2.55 given that formula over here and plugging in all of our values. So when we did it by calculator, we got 2.54999. When we did it with the table and the formula, we got 2.55. So same value, 2 different methods. So because this hypothesis test is right-tailed, why is it right-tailed? It has to do with what we're comparing it to. Because it's a greater than symbol, it's right-tailed. With a test statistic of 2.55, the p-value is the area to the right of z equals 2.55. Referring to table A2, the cumulative area to the left of 2.55 is 0.9946. So we want the area to the right of that. So we have to do 1 minus 0.9946, which equals 0.0054. So we get a p-value of 0.0054. Again, that showed up over here as well. So from here, we have our normal distribution, z equals 0 right in the middle, and our midpoint is going to give it a 0.5, meaning that there's 50% of the area to the left and 50% of the area to the right. And our critical values are over here. Our p hat is 545 divided by 1009, or a z value of 2.55, and our p value is 0.0054. So because the p-value of 0.0054 is less than or equal to the significance level of 0.05, we can reject the null hypothesis. That's the big key right there. So because we are rejecting the null hypothesis, that means that we support the alternative hypothesis. P is greater than 0.5. So we conclude that there is sufficient sample evidence to support the claim that more than half of consumers are uncomfortable with drone deliveries. So that was the p-value method. Now we are going to solve the same problem using the critical value method. So for the critical value method, steps 1 through 5 are the same as the previous method. Step 6 is where it differs. The test statistic is computed to be z equals 2.55. We got that right here, and we also got it from the calculator over here. With the critical value method, we now find the critical values. Again, this is a right tail test, so the area of the critical region is an area of alpha equals 0.05 in the right tail. Referring to table A2 and applying the method 6.1, we find that the critical value is 1.645, which is the boundary of the critical region. So we now have a critical value of 1.645. Our alpha is 0.05, and our test statistic is 2.55. So because the test statistic does fall within the critical region, we reject the null hypothesis. Because we reject the null hypothesis, we conclude that there is sufficient sample evidence to support the claim that most consumers are uncomfortable with drone deliveries. So both the p-value method and the critical value method both had the same conclusion. So finally, the confidence interval method, the claim that the majority of consumers are not comfortable with drone deliveries, can be tested with a 0.05 significance level by constructing a 90% confidence interval. So the 90% confidence interval estimate of the population proportion is found by the sample data of n equals 1009 and x is 545. So using the methods of section 7.1, we get that the population proportion will fall between 0.514 and 0.566, and the entire range of values in this confidence interval region is greater than 0.5. So since we are interested in a value of 0.5, and both our lower limit and upper limit is outside and greater than that 0.5 region, we are 90% confident that the limits of 0.514 and 0.566 contain the true value of the population proportion. So the sample data appear to support the claim that most consumers are uncomfortable with drone delivery. So 3 methods now, 2 that I would like to use, the p-value method and the critical value, and we also did it using the confidence interval method. So finding the number of successes x. When using technology for hypothesis tests of proportions, we usually must enter the sample size n and the number of successes x. But in real applications, the sample proportion p hat is often given instead of x. So you just have to know that the number of successes can be found by doing x equals n times p hat. So in the next example, the result of 5,587.712 must be rounded up to the nearest whole number of adults, meaning 5588. So just quick example, a study of sleeping was described in a magazine, and it concluded that 29.2% of 19,136 American adults have sleepwalked. What is the actual number of adults who have sleepwalked? Well, it'll just be 29% or 29.2% of 19,136, which would give us 5,587, but we can't have 0.712 adults, so we round that up to the next whole number. Last example for this section. Using the same sleepwalking data from the previous example, would a reporter be justified in stating that, the claim is here, fewer than 30% of adults have sleepwalked? So the sample had 29.2% of adults sleepwalking. So can you claim that fewer than 30% of adults sleepwalk? Okay. We'll use a 0.05 significance level to test the claim. And the proportion of those who have sleepwalked is less than 0.3. All right, let's do this. First, requirement check. The requirements are all satisfied. Okay, next. The original claim is expressed in symbolic form. We are saying that the population proportion is less than 0.3. The opposite claim of that statement would be, well, if it's not less than 0.3, it's greater than or equal to 0.3. So we have our null hypothesis. Again, the null hypothesis will include an equal sign. We are saying that the null hypothesis, P equals 0.3. The alternative hypothesis is going to be the actual original claim, which is that P is less than 0.3. The significance level is 0.05, and because the claim involves the proportion P, we are interested in P hat, and a sampling distribution can be approximated by a normal distribution. Okay, in this case, we will use StatCrunch to get our values. You can also use your TI-84 or the book for the table. And then you will find that the Z value is going to be negative 2.41, and the P value is 0.008. And I also included a link to a YouTube video if you kind of wanted to see how you can do that on using StatCrunch. Or you can do it using the formula. Again, the formula would give it a value of negative 2.41, which is the same as what StatCrunch gave us. So for this left tail test, the p-value is the area to the left of the test statistic. So using table A2, we see that the area of left is of negative 2.41 is 0.008, so that's the p-value. So because the p-value of 0.0080 is less than or equal to 0.05, we reject the null hypothesis. If we reject the null hypothesis, we're looking at the alternative hypothesis. Therefore, we conclude that there is sufficient evidence to support the claim that fewer than 30% of adults have sleepwalked.